Okay, so Phil Hackney has kindly agreed to give a talk in the seminar. The title is A Seagull Model for Modular Operads. Take it away, Phil.
Thanks, David, and thanks for organizing this. I feel like these have been really nice seminars so far. Okay, so here we are at the fringes of MSRI. This picture is from this morning. It's the first time I've actually seen this view, although apparently David has seen it before. He knows the spot, he told me. Right, and so what are we going to get up to today? I think in a large part, Aaron Mazel-G gave a talk a few weeks ago, and he talked about a graph category, and it looked really nice to me and felt very similar. So I thought I would give a talk about a graph category as well. So here's a brief outline of what I'd like to talk about today. So we're going to be talking a bit about modular operads, and I'll give an introduction to sort of what I mean by that. We'll say what we mean by graphs, and maybe talk about embeddings of graphs. And then I'll present this graph category U. And I'll also talk about some additional structure. That's present on this. And finally, we'll discuss a little bit about tree-sheaves and the Seagull condition. And maybe I should say a word about motivation before. I think the main motivation for maybe some of the theorems I'll present and some of the constructions is an ongoing project of Pedro Boavida, Shafwa Harel, and Marcy Robertson on pro-finite completion of GT, of the Grothendieck technical group. So they're looking at, their idea is to look at some pro-finite completion of some modular operad and see how it acts, and generally taking pro-finite completion of something breaks any kind of strict structure you have, and so they end up with something that's just weak. So they actually had they need some weak version of modular operad, and that's what we'll be discussing today. Okay, so first, what is a modular operad? And this is going to be in a cartoon picture kind of way. So first off, you have a bunch of objects. Let's call them M0, M1, M2. And I'm thinking about these as follows. So something like, here's maybe how I'd picture an element in M5. So I want to think about it as having several different legs that I can deal with, or 5 of them actually. And these sets that constitute this, maybe the standard kind of example is to think about maybe some surface here with this number of boundary components. Maybe it has some genus. So I think the classical example is some kind of moduli space of curves with n will have n marked points, and maybe there's an additional grading by genus or something. But this is a kind of example to keep in mind. And so there's two kinds of structure that I really want to emphasize. The first is a sort of cyclic operad structure. And that amounts to having j times k maps from mj times mk to mj plus k minus 2. And if I draw another one of these, so this one's in M3, and maybe I'll put a little surface there as well. What this amounts to, the j times k business, is that I have to pick an edge from each of these. So maybe I pick this one, and maybe I pick this one. And then I glue those together along those edges. So there's a choice there. And if I draw these in, well, this is really putting a cylinder in there as well. So I get a new surface out, and this gives me something in M1, 2, 3, 4, 5, 6, M6. So that seems to check. But the other part of the structure is that we have something like j times j minus 1 contractions from mj to mj minus 2. And what is this? Well, these correspond to self-gluings. So again, we pick two edges, and then we glue these edges together, and we can again fill in a cylinder. So these are, just start with one thing, but you produce something of with fewer inputs. And we've used two of those up. Of course, generally when we do this, there's a bunch of other structure. There's some symmetric group actions, there's units maybe. Maybe an additional grading based on genus, maybe some colorings, which we'll get to later. For instance, maybe I want to specify some of these boundary components as inputs and some of them as outputs, and I want to keep track of that and only glue appropriately, or maybe that would be possible with colorings, or maybe I want to do some kind of open-closed kind of thing where some of the boundary components are circles and some of them are intervals, something like that. But
I have a quick question. Yeah. Should I think of the sequence of M's as spaces or sets, or could they be something linear like vector spaces?
So in general, they could be vector spaces, and this is how they originally developed. But I want to be agnostic about it here. Today, I think I really want to think about sets and spaces for most of the statements I'm going to make. But hopefully there's some idea about how to extend to other situations we'll talk about.
Gotcha, thanks.
Can I leap in here? This is Ezra.
Sure.
For a second, I think any symmetric monoidal category where the tensor product is, well, let's say closed symmetric monoidal category.
Maybe compact, do you want? Or you're talking about where the MIs can live?
The target, yeah. It doesn't just have to be vector spaces. It could, I mean, really any.
Yeah, absolutely.
Yeah, so basically a symmetric monoidal category, probably need that condition on the tensor product.
I'll just pipe up. I see a question in the chat from David Yetter. Why j times j minus 1, not j choose 2?
So I think when I pick the first, I have j choices, and then I have j minus 1 things left over. Yeah, maybe it is j choose 2. Yeah, I agree. Thank you. Any other questions? Okay.
I want to pipe up again. I'm sorry, this is Ezra again. I want to pipe up again. If you've chosen an order on the legs, then yeah, j choose 2. But until you've chosen that order, then your j times j minus 1 is more agnostic. But there are going to be relations among those, that's all. But until you can't say, yeah, okay. A choice function would allow you to reduce it to j choose 2. But yeah.
Yeah, and I haven't been very careful about whether I've chosen orderings on anything. I'm just, yeah, I think for pictures, just pictures right now. Great. So as I said, I'd start with some main theorems. And the first theorem is a kind of nerve theorem. And what this says is that the inclusion of, well, I'm going to describe some category of graphs today, and some structure on that category. And this theorem says that the inclusion of this into modular operads, so basically every graph is going to freely determine some colored modular operad. The exact notion I'm discussing has been called compact symmetric multi-category by others. That terminology was introduced by André Girard and Joachim Koch. If I look at the associated singular functor, it's fully faithful, and its essential image consists of Seagull presheaves. Oh, am I not sharing this screen anymore?
It has not scrolled for a little while yet.
Yeah, so if I seem stuck on the wrong screen,
Great.
Please let me know. I need to pay more attention.
Good.
This seems to be similar to the problem David Gepner was having, where sometimes it wasn't updating.
Yeah, that was really annoying.
Right, so every graph is going to actually give me some kind of modular operad, and I can look at this associated singular functor and classify its essential image. So one consequence of this is that we don't really need to know what modular operads are precisely before this talk, because we could take this as a definition if you don't already know what it is. And a corollary of this is that if, so I haven't quite said what this functor is or what this category is, that's all going to come later, maybe not the functor. But if instead of looking at whatever U that I define here, I look at the full subcategory of modular operads, you again get a singular functor with a similar kind of characterization. So this corollary, this was announced as a theorem back in 2011, and I think that the proof of this is Sophie Rayner in her thesis. She really followed the kind of the perspective of Joël and Koch in how to build this up using Weber theory in a very careful way. So it took a while, and it's also a consequence of the theorem above, using some density results, basically following something I learned from a paper of Steve Lack and Simona Pevoli. But it did take a while for a proof of this to appear. So the second theorem I want to talk about is the sort of more homotopical version. And this is saying that if I look at simplicial U pre-sheaves, I can again look at some kind of Seagull condition, and I can identify things as the fibrant objects of this as some sort of weak modular operads where multiplication is only defined up to homotopy, but in a coherent and structured way. So we'll come back to this theorem later.
Sorry, can I ask a quick question? So this is Ezra again. Oh,
yep.
Yeah, so X1, so that corresponds to just vertices with a single leg coming out of them.
So by this, I'm meaning sort of a, maybe I should have written E here.
Oh, this is not the notation that you began with modular. You began with modular operads were X1, X2, X3, and so on.
Yeah, so here I really mean, so okay. This is the graph that looks like what I drew. So I should call this like a free living edge. There are no vertices here.
Oh, so this is X0 in the previous notation. Is that?
I would write, so I would say X0 is X of a graph that looks like this.
Yes.
Whereas X of a graph that looks like this, that doesn't show up. This is supposed to be like the set of colors.
Oh, this is just a graph with no vertices.
Yeah, it wasn't a 1. Thank you.
Oh, good. Okay.
Maybe I should say a little bit about what graphs are, since to make sure. Right, that did show up. Now I'm nervous that nothing's going to show up. So what do I mean by graphs? So generally, I mean, we're going to have a collection of vertices. I'll draw them in pink because I drew them in pink below. We're going to have some edges between vertices. I want to allow multiple edges between vertices and also loops. But I also want to allow kind of loose ends that don't have vertices attached at one end. This would include things like just this free living edge with no vertices at all. I'd like to include, well, I'd also like to include things like a circle And of course, you can have circles with a vertex on them. And I can have edges with a vertex and so on. Okay, so these are all just some examples. One way of encoding what I'm thinking about is that you have a space and then you have some discrete subspace of finite number of vertices, so that the complement of that is some one manifold. That would allow us to include this circle in our example when V is empty. And then you can recover the set of edges as the set of components of this complement. So think about deleting those all those pink pieces and what shows up. And I think it's a little bit weird to write down something like this. Maybe this doesn't match what you would think about as a graph, even if you're thinking about having loose ends, but it's sort of important for the kind of modular operad gluings that we're going to discuss. Right, so if I have such a thing, what's some information that I can glean from it? Well, first of all, if I look near any of the vertices, I can look at these sort of germs of edges that come into the vertex. So here's two examples. So the one on the left has 4 things, and the one on the right has looks like 6. But notice that I don't actually mean edges, because here where I have this loop, I'm sort of seeing the same edge appear twice, once coming in both sides. Okay, so maybe a better thing to think about if I want to recover the structure of a graph somehow combinatorially is to think about the set of oriented edges. And that admits, well, maybe a partially defined map into the set of vertices, saying where that oriented edge points to. Alternatively, I could structure this using a diagram like this, where here this I is an involution that reverses the orientation of an oriented edge. And D are exactly the places, the oriented edges that point towards a vertex. And T tells us which vertex they point towards. And so I can recover here these neighborhoods that I've drawn as pre-images of a vertex. I can also recover this sort of the boundary of the graph as exactly those oriented edges that don't point towards any vertex. Okay. So we could see a graph as some kind of functor from a category of the right shape. Maybe I is fixed point free. And S is a monomorphism. And that's useful sometimes to repackage the information this way. maybe give a couple examples of how you could see this. So for the first example, if I have any finite set, I can look at a kind of star on that finite set, pictured here. And it has as its edges just the set Z, Z. And so its oriented edges are like 2 copies. And I'll think about this as maybe maybe I'll write prime for the second copy of an element Z. And one vertex. So in this picture, we have 10 oriented edges or arcs and 5 edges and 1 vertex. Another example is this free living edge E, which it has 1 edge, so it's going to have 2 arcs, and it doesn't have any vertices, so the diagram would look like this. And here I should emphasize that we sort of have 2 boundary components, and that's how we're thinking about those. An unfortunate thing is that the circle is no longer an example. It had just a single edge. And if I encode that information, it looks exactly like E, but this has the wrong boundary. So somehow I had said the boundary is the things that don't point to as a vertex, but that's not true in this case. So this is a downside to this structure that I've written down. But another example we do have is we have all these kind of circles with at least 1 vertex on them, and you can describe them this way. Okay, before I give the full definition of what this graph category is, I'll say what an embedding of connected graphs is. So a map of graphs should be some kind of natural transformation. So here I have 2 graphs, G and G prime. And the embedding, well, first of all, I want to have good compatibility at each vertex. So I have a map of vertices, and I want a vertex of valence k to map to a vertex of valence k. So the first thing I want is that right-hand square to be a pullback square. That will ensure that. The second thing I want is this V to V prime to be an inclusion, a monomorphism. So as an example, in this graph, how do I determine an embedding? Well, or in general, how do I determine an embedding? I'll pick some vertices. Maybe I'll take these. And then I'll take, for sure, all the edges that go between them, or I better end up with something connected at the end. And maybe I can pick some others. So this part that's highlighted in blue here would be something that embeds into the bigger graph. And I guess one thing to emphasize, a warning here, Embeddings are not monomorphisms. Not always. So for example, in the picture that I just drew, if I look over here, in the shaded part, there's somehow two edges, this edge and this edge, where in the original graph there was only one. Okay, and this is going to actually mean that I'm not getting an inclusion over on the arc side of the diagram here. Okay. So let's look at the canonical examples of embeddings. So if I have any graph and I have any vertex in the graph, there's a natural embedding of essentially the star at that vertex into the graph itself. This is a big part of why these aren't supposed to be monomorphisms, because it's just not in examples like this, where here I have two arcs, C and D, that are related by this involution, and then here I have kind of four arcs that hit those two. We can also include edges into a graph. So for every edge, so an edge is like a an orbit of this involution I on the oriented edges. So whenever I have such a thing, I can write down a natural kind of, actually in this case, it will be a monomorphism, but an embedding. So I write these down particularly because they'll be useful to us later. So I'd like to make an observation about viewing graphs this way. And I don't think it's particularly deep, but if I have any graph, right, we have some set of edges, we have some set of vertices, we have some set of arcs, and so on. And I view it as a functor from this scripty G category into sets. I can actually write that as a co-equalizer in a particular way. So, I mean, maybe there's multiple ways to do this. Anytime I choose an orientation for each internal edge, then that will tell me a decomposition like this. So as an example, I'm only choosing orientations here. If I look at this graph, then maybe I shouldn't have used E and E prime, but I have two maps. So the top map is going to go to star V, and the bottom map is going to go to star W, just the inclusion you would expect. And I also have E prime, which now goes the other way. So here the top map, because it's pointing towards W, is going to go into there. And this map is going to go into there. And then this co-equalizer is just this graph G. So the reason I'm presenting this is because I want to modify this picture. And I think I've left a little too much on this slide. And the key to that is I need to talk about graph substitution. And what is this roughly? Well, I start with some graph G as maybe as depicted here. And then in each of these nodes, I blow them up to some kind of other graphs. So I stick in a graph to each of them. And here I'm generally, from now on, I'm only thinking about connected graphs. And if I erase the pink circles, I end up with a new graph. So this somehow required some bijection between the boundaries of these graphs that I plugged in there and the neighborhoods of the original graphs that I started with. And this warning down here is really talking about that not all such graph substitutions are valid in the formalism we've written down, because if I took this and tried to stick in just this edge into each of those, I'd end up with a circle, and then that's sort of a problem for us right now. I mean, this is a thing you need to be able to do, but that's one needs to be careful. So the reason I wrote the observation on the previous slide is you can see this construction of graph substitution very concretely, just as some co-equalizer. So the top part of this slide was on the previous slide, two back. But now to define a graph substitution, this is sort of the data of some isomorphisms, some graphs, which I'll call HV. And then these isomorphisms, more or less going to the neighborhood of V in the big graph G. Okay, and if I do that, then what I'm able to do is just replace this this star V up here with the HV down here, and tweak these two maps in my co-equalizer a little bit, and then that works out. Usually it works out. So this more or less works, except in the bad case that I drew on the previous slide.
So Philippe, this is Muriel Liverne speaking.
Yeah.
Can you explain or describe the maps from the left graphs, internal edges to HV?
Yeah, so let me draw a picture. Or actually, let me copy the picture that I had, and I'll expand it. So this was our picture that we had before. And was this one okay? And so now what's going on? Well, maybe I can label things a little bit more. So I'm going to I'll call this A, that one that's pointing towards V. I'll call this IA, I'll call this B, and I'll call this IB. So IA points towards W and IB points towards V. Okay, and now I take some other graphs. Maybe H looks like this, and maybe HV looks like this. And I have to draw in the I have to say something about what the bijections between the boundaries are, but maybe what I'll say here is that when I'm thinking about this picture, I'm using the data of those bijections. So this is what I started with. And more or less, this E is going to here. So the top map takes what I'm describing what the top map does on E, and in HV it's going to map A to this edge that's pointing towards the vertex of HV, or alternatively it's mapping IA to the boundary component of HV, the boundary element of HV. And the bottom map is doing something like this. It's mapping IA to the thing pointing towards that vertex, and it's mapping A to the boundary thing of the original. So this is the way that these things are sort of being glued together. And I won't draw B, but we can imagine how a B would go. I mean, I could draw B if you want. Is that helpful?
It's okay, thank you, yeah.
Okay. Okay, so I think we're ready to define what a graphical map is, and here's a definition. So this is expanding on the notion of embedding that we had before, which are examples. So remember, in an embedding, you have a map on arcs. That's a map preserving some involution. And so here you still have a map on arcs preserving some involution. And before, you had a map from, let's say, V to V prime, was part of the data. Here you don't have a map from V to V prime, but rather you have a map from V to sort of the embeddings of G prime. So the things that have codomain G prime. And V prime sits inside of these embeddings. So embeddings are examples of these. And there are some conditions. I think maybe the most important condition is the generalization of what it means to have the diagram, the map of diagrams that I wrote down before, be a pullback. So the analog of this pullback condition, preservation of neighborhoods somehow. And that's 2. So somehow, if I look at the boundary around some vertex V, the neighborhood around the vertex V, that should be in bijection with the neighborhood around the thing. And I'll draw a picture in a second. One is sort of preserving the kind of thing that you already saw in embeddings, that you're not, you know, this is a kind of generalization of the monomorphism condition on vertices. And the last condition is a collapse condition, and I'll give a picture on the next slide. So this says if the boundary of your domain is empty, then you can't send every vertex to just essentially an edge in the target. So first I'll give a nice example and say how I view such a thing. Or how I think about them. So first of all, there's supposed to be some map on oriented edges or arcs. I'm not going to write that down, but what I will say is what happens on vertices. So each vertex should get a subgraph associated to it, or some embedding. And I'm going to draw them like this. So maybe this, maybe I won't draw an arrow. But these are the embeddings that are showing up. So the highlighted areas are 3 different embeddings into the target graph. And the 3 vertices should each go to one of those. Okay, so it's fine to send a vertex to just an edge in your target. It's fine to send it to something bigger. And it's fine to send it to just another vertex, essentially, your target. Okay, so this is maybe a typical picture. right? And the last condition that we had was essentially to prevent pictures like this. So there's if I start with a circle with 3 nodes on it, I could send each of those vertices to just an edge, which is an embedding, embeds in the edge. That's perfectly fine, but this is not the sort of thing that we expect. And this comes down to a lack of control over the, well, basically that the diagrams for these two are the same. They're sort of indistinguishable. What we really like is a map going down to the down right, but we don't have such a thing. And finally, finishing off what this category U is, composition in this thing is defined by a graph substitution. So if I have 2 such maps, as indicated here, I've kind of drawn them below what each one does. So maybe I should highlight for the first one. Yeah,
Phil, this is David. So I for one, am not seeing the changes you're making in the document.
I've lost it again. Better? Is this okay?
That's what I was looking at. Oh, yes, great. There we go.
Thank you for letting me know. I didn't notice. So I won't say too much about this, but essentially composition comes down to being able to substitute, and substituting in 2 ways works out fine. So this first map is doing something like this. No. So this first map expands these vertices out like I've drawn here. And then the second map expands vertices like this. This doesn't expand anything, this doesn't expand anything, and this one just goes to an edge. And then down here we've expanded this somehow. Be more like this.
I just want to check. So the choice of which edge there is part of the definition of the morphism, right? You hesitated which edge you were going to choose, but the choice of the 2 edges is different cases, isn't it?
Which edge do you mean?
Just then, you had the 2 vertices, and you've highlighted one of the edges between them. And
right, so
you have to choose which one, but the choice of which one is part of the data.
Yes, and I should emphasize this one. This is also highlighted. So this top vertex maps to that top vertex.
Yeah.
Yeah, but yeah, it's all determined. Really, I'm trying to reconstruct this.
What I'm trying to say is usually the highlighting is fairly transparent, but not always. Oh, I see. The picture at the bottom tells us.
Yeah.
I didn't notice it. Oh.
I'm trying to reproduce this.
Okay.
So the composite from left to right is really taking these three green embeddings in the target. So that's a sort of graph substitution kind of operation. I think I should mention that that the simplicial category delta includes into U this is a faithful embedding. So the way to do this is to think about each of the objects of delta as a graph where the number here denotes the number of vertices in the graph. And the morphisms that I've written down before are maybe more morphisms than you have in delta. So each of these I can think about as coming with an orientation. And the maps in delta are exactly the ones that preserve that orientation. So in general, if I looked at maps in U between such linear graphs, well, they're maps of these finite sets that are either order preserving or order reversing. And they know which one they are. For example, U let's say the automorphisms of this edge well, there are two of them, right? There's either the flip or the not flip. So somehow you have to remember whether you were order preserving or order reversing. I guess this only makes a difference for constant functions from K to L. And similarly, you can embed the dendroidal category or include the dendroidal category into here, but it's only faithful. So somehow, in the context of the first theorem, where somehow I have some, I don't have underlying categories of modular operads, rather I have some kind of underlying involutive category, and that's attributed to this kind of flip. Okay, so where are we at? We have this category of undirected connected graphs with these graph morphisms. We have several interesting subcategories. I can look at the embeddings. We've already discussed that. I can look at boundary preserving maps. These are also called active. And maybe the embeddings could be called inert. We have two interesting classes of active maps. We have the ones where the map on arcs is surjective, and we have the one where maps on arcs is injective. And finally, we have something that is, let's say, generated by embeddings and generated by these active maps that are also injective. There's other descriptions of this, but one issue is that these are not necessarily injective on arcs. As we've seen before. Otherwise, we could just say this U plus is consists of the things that are injective on arcs.
Sorry, oh, sorry.
Is it okay?
Sure, yep.
So here's a couple propositions about this category. So in this structure that we've just seen. So first of all, this pair consisting of these active maps and these embeddings, this is an orthogonal factorization system on U. So every map factors uniquely as an active map followed by an embedding. And you could sort of imagine how to do that. You basically take the factorization looks like this. If I have G to G prime, it should factor through GHV. So I've just blown up all those vertices in the right way, and this left downward map is active because whenever you have a graph substitution, you always maintain your boundary, and this other map is an embedding, gluing together all those other embeddings from each of these. So here, yeah, maybe I'll leave it at that. And one consequence of this is that you can apply algebraic patterns machinery of Hangyi Chu and Runa Hoxang to get a good notion of Segal stuff. And if anyone knows about this, you could take either your elementaries to be either the stars or the stars and the edges. And you'll get something nice either way. but this preprint didn't exist when we wrote the paper, so that's the second proposition is that there's a generalized Reedy category structure on this category U, where the degree function for a graph is given by the number of vertices plus the number of internal edges. So one consequence of this is that we get a model structure on this category presheaves for any, let's say, cofibrantly generated model category M. I'll just write nice enough because maybe it's cofibrantly generated is too strong. This will be equivalent to the projective model structure, but it's somehow much easier to be cofibrant here. So this is very helpful. And we'll see in a second why this is actually helpful for us. Okay, so I said that proposition 1 will allow you to apply some machinery of Chu and Hoaxang to this. I can unravel some of that, or how this would look in this case. So recall that we had this description of a graph. I can write it as a co-equalizer. I could just convert this over to the setting of representable presheaves. So wherever I saw an E, I just replace it with a representable at E. Whenever I saw one of these stars, I replace it with this representable at star. And now the co-equalizer isn't G anymore, but it's this so-called Segal core at G. I'm taking the co-equalizer in a different category. So this, I should emphasize also, this is not a co-equalizer in U. It's only a co-equalizer in here. These objects don't even exist in U because they're not connected. Okay, and of course each of these U star V's admits a map to U of G, and the U of E's factor, also admit maps. And so we end up with a map from the Segal core of G to the representable object of G. And remember, this is of blank into G. Right, so what is the Seagull condition? So this says, if I take all of those Segal core inclusions, so an object X, a presheaf X is going to be Segal if it's local with respect to all of those. And this right-hand side, this is some kind of equalizer of sets. And you just ask that this be a bijection, these natural maps. So for us, the special case is maybe instead of thinking about a complicated limit, let's think about when all of those, the value at the edges is just a point. So this equalizer is going to become just a product. And so we're insisting that if I look at the value of x at some graph G, it's determined by the value of the pre-sheaf at each of the vertices, essentially. And we can use this to define some structure, because here we have a map from X to a star on the number of boundary components of G. So this gives us some kind of operation that takes these decorations at the vertices and produces something here. And this should define us some kind of modular operad. So let's look at how this goes in small graphs. So if I look at graphs with one internal edge, maybe I'll just draw a couple pictures. So here's a graph with one internal edge. Here's another graph with one internal edge. So in this case, we end up with something like this graph determines a bijection to, let's say, star 4 times x star 3. And then I have this active map going to x of star 5. Okay, and this is defining one of our cyclic operad kind of composition maps from before. Whereas here, well, now I have this weird sort of complicated graph, G, but its Segal core is just, or it's, it only has one vertex that has valence 7. And this goes to x star 5 by that active map. So this is defining contraction. Okay, and an associativity kind of conditions. These come from looking at graphs that have two internal edges. So if we jump back to theorem from the beginning, this is more or less, you know, a chunk of the thinking that goes into this. And we could have dealt with something a little more skeletal. I guess we don't, you know, in the strict case, we don't have to deal with graphs that have too many internal edges in order to get a result like this.
Can I just ask, so in the previous page, oh, not previous, but the...
This one?
Yeah, so when you contracted the loop, There are two different, as we discussed on the first page of the talk, there are two contractions, I think, or does that not happen here?
I think it's just having the pair is you're just picking the pair of the edges.
I see. Okay. But there's no need. We don't need any equivariance condition at this moment.
No.
Okay.
Yeah, I'm suppressing all of that stuff, but it's all sort of hiding here in the it's hiding here in the isomorphisms in the category U, really.
Right.
And I guess we also had the second theorem. Oops. Here. So we should maybe shift our attention to simplicial sets and say what Segal means. And here I've just recopied this previous definition, but maybe let's adapt it. So let's now look at something that lives in simplicial sets instead of sets. And maybe Ham isn't the right thing anymore. I think it's fine to regard these representables as sort of simplicial presheaves that are discrete in one other direction. But let's replace these with map. And let's not have bijections. That seems bad. Let's replace that with weak equivalence. So these are both sets now, or both spaces. Okay, so now our picture becomes something more like this. So, let's say when, for simplicity, when x of the edge is a point again, these maps now become just weak equivalences, but we still have this map as usual. So if we picked, inverses to this, this would give us some kind of multiplication, but in general, that's only, weakly defined in some way. So there's not really a map this way, or maybe there's many, depending on what kind of map that equivalence is. I should emphasize that this side is still this is still a limit. But maybe I won't make too big a deal of that. I guess I have a proof sketch slide, but maybe I'll just say quickly is use the Reedy model structure. And localize at the Segal core inclusions. And sort of the 0 into U of E, and interpret what local means. So this might require you to have to do something like argue that this Segal core of G is cofibrant, for example, in order to get rid of homotopy mapping spaces and just have honest mapping spaces. Right, so maybe I'll end with just a couple other questions. One thing I was thinking about leading up to this is to take this topological picture more seriously. So I described at the very, early on in the talk that these graphs could be considered as spaces with some subset of vertices, and I could conceivably look at so is there some topological category with, let's write C with pi 0 C equals U, for example, where now I've replaced these sort of combinatorial kind of embeddings with actual embeddings. It'd be cool to see this work over other ground categories. So historically, or generally doing Seagull conditions isn't going to really work over other kind of ground categories, but I'm thinking about something like David and Runa's work, or Chu and Runa's work on on doing this kind of thing for enriched infinity categories, things like that. And finally, there's another approach which maybe needs two to work, is to compare with Ben Ward's approach to infinity modular operads. So these are just a few ideas. So Ben Ward showed that some colored operad governing modular operads is Kazul, and is able to use that to define such a thing. Okay, thanks.